Could the universe's most basic building block be not a particle or a wave, but a piece of information? In a digital view of reality, classical bits, zeros, and ones encode states. But quantum mechanics introduces the qubit, which can be both 0 and 1 at once. The minimum bit hypothesis asks, is the qubit the true atom of existence, or does something even more elementary, pure information, lie beneath both bits and qubits? What is a classical bit? This is the simplest piece of data on or off, true or false. In computing and in some interpretations of physics, you can imagine the world as a grand network of switches flipping between two states, each flip storing or processing one bit of information. This tidy picture, however, fails to capture the weirdness of quantum superposition. How does a qubit differ from a bit? A qubit can inhabit multiple states at once until you look at it, both 0 and 1 in superposition, and can become entangled with other qubits so their fates intertwine instantly across distance. This vastly richer structure means that a handful of qubits can encode far more possibilities than the same number of classical bits, suggesting that if reality runs on information, it may prefer quantum bits. Could information be more fundamental than matter? Physics veteran John Wheeler coined it from bit to propose that every physical event boils down to a yes/no question at its core. Instead of particles bouncing around, the universe might be answering binary questions, with each answer knitting together space-time and forces. If true, information becomes the bedrock, and matter springs from the answers. How might quantum gravity redefine the smallest unit? Theories like loop quantum gravity picture spacetime itself as quantized, woven from tiny loops that carry fixed bits of information. In such frameworks, even qubits get replaced by discrete chunks of geometry, hinting at an ultimate unit smaller than the qubit, but still informational at heart. Can we test whether reality is made of bits or qubits? Quantum computers push the limits of bit versus qubit behavior, while precision measurements of gravity at microscopic scales using interferometers or particle collisions seek cracks in continuous timescale. Any unexpected decoherence or energy leakage could signal the granularity of information itself. So what's the bigger perspective for curious beginners? Whether the smallest thing is a classical bit, a qubit, or a deeper informational kernel, the minimum bit hypothesis challenges us to rethink existence as computation. In the quest to unite quantum mechanics and gravity, asking what is information might unlock the final secret of reality, showing that the universe is not just made of matter and energy, but of knowledge itself. The minimum bit hypothesis posits that information, not particles or fields, is the most fundamental constituent of reality. In this view, the universe's degrees of freedom are encoded in binary choices, bits, or quantum superpositions thereof, qubits, with physical phenomena emerging from the processing and transfer of these elementary informational units. This challenges traditional ontologies by suggesting that information is ontologically primary, not merely descriptive. In digital physics models, for instance, space-time and matter are reconstructed from networks of interacting bits, updating according to simple rules, much like building an entire world inside a computer game where every object and event arises from underlying sequences of zeros and ones. A classical bit represents a definite 0 or 1, forming the basis of conventional computing and information theory, while a qubit can exist in a superposition of 0 and 1 states until measured, encoding more information per physical carrier. The minimum bit hypothesis probes whether reality relies on classical bits, quantum qubits, or some deeper unit of informational structure. And clarifying this distinction is key to understanding whether the universe is fundamentally digital, quantum, or a synthesis of both. Quantum computers, for example, exploit qubits, superpositions, and entanglement to perform calculations exponentially faster than classical computers can, much like comparing a simple on-off light switch to a dimmer capable of holding every possible brightness until measurement locks it in. At the microscopic level, quantum systems encode information in the amplitudes and phases of their wave functions, where physical states correspond to vectors in a Hilbert space whose dimensionality determines how many qubits are required for their description. Measurements collapse these states, yielding classical bits of outcome information while destroying their superpositions. Entanglement distributes information non-locally, so that knowing the state of one qubit instantly informs about its entangled partner, even across vast distances. A pair of entangled photons, for instance, carries a single qubit of joint information, behaving like two perfectly synchronized clocks in different rooms. where reading one instantly reveals the other's time without directly observing it. Information acquisition is fundamentally tied to thermodynamic cost, as described by Landauer's principle, which states that erasing one bit of information dissipates a minimum amount of heat. Quantum measurement ties information gain directly to wave function collapse, causing entropy to increase elsewhere in the environment to preserve overall thermodynamic balance. Thus, information flow is inseparable from energy and entropy dynamics, anchoring the minimum bit hypothesis in physical law rather than abstraction. Erasing just one bit of data at room temperature must dissipate at least about 3 zeptojoules of heat, much like clearing a chalkboard where one must expend energy to wipe away the writing and reset it to blank. Whatever the physical substrate for these fundamental bits, be it electron spins, photon polarizations, or more exotic topological structures, it must support universal computation to replicate all physical phenomena. The Church-Turing-Deutsch principle generalizes this idea by asserting that any physically possible process can be simulated by a universal quantum computer. Hence, the substrate of reality must possess the capacity for universal information processing, reinforcing the notion that physics itself could be computation unfolding. Simulating a hydrogen atom's energy levels, for instance, requires qubits encoding its quantum state, evolving under the Schrödinger equation, much like ensuring that every hardware piece in a computer can, in principle, run any software if properly programmed. Deepening this informational framework, the holographic principle suggests that the maximum amount of information contained within a region scales with its boundary area, not its volume, implying a fundamental upper limit on bits per spatial region. Nonlinear gravitational effects enforce this bound, preventing any system from exceeding the information density that would trigger gravitational collapse into a black hole. Consequentially, space-time geometry and information density are co-determined, embedding information limits directly into the structure of reality. For example, a black hole with event horizon area A contains roughly A divided by 4 Planck areas worth of bits, akin to a bookstore where the number of books that can be cataloged depends only on the surface area of the shelves, not their stacking depth. If bits or qubits truly constitute the smallest building blocks of reality, then physical laws themselves reduce to information processing rules, potentially uniting computation with dynamics in a profound way. This perspective fuels modern efforts to derive spacetime and gravity from entanglement networks, as seen in tensor network models where geometry and curvature emerge from the pattern of informational connections. It reframes fundamental interactions not as forces between particles, but as exchanges of information across an evolving computational structure. Discovering that the pattern of a quilt dictates the shape of the blanket itself, rather than the blanket imposing the pattern, captures the transformative insight offered by the minimum bit hypothesis. Despite these tantalizing ideas, formidable challenges remain in validating such informational models of reality. No direct experiment yet counts the ultimate information quanta of space, and theoretical proposals span a vast range of potential bit substrates. Reconciling discrete informational structures with the apparent continuum of observed spacetime and defining what constitutes an irreducible bit in a quantum gravitational regime are major unresolved issues. Efforts to detect spacetime discreteness, such as analyzing gamma-ray burst timing for Planck scale jitter, have so far found no definitive evidence, much like trying to resolve the individual grains of a distant beach by simply watching the waves. Nevertheless, future directions offer hope. Advances in quantum information theory, quantum gravity proposals, and high-precision cosmology may converge to reveal whether bits or qubits truly underlie the universe. Laboratory realizations of programmable quantum simulators create experimental platforms for testing information-centric models of spacetime, effectively building toy universes to probe how geometry and physics emerge from computational dynamics. Proposed table talk experiments using superconducting qubit arrays to simulate small quantum geometries could provide critical insights akin to hacking the firmware of reality itself, rewriting the very code that underpins space, time, and matter.